Okay, I just want to thank the organizers again. This has been a marvelous meeting, and it's really enjoyed the discussions and recent discussions with some of the experts in magnetic fields as well who have come. So this is about tunneling and actually the absence of tunneling as well in quantum magnetic systems. And what I'll talk about is based on a number of articles. First, an article on tight binding with Jacob Shapiro in magnetic systems, and then subsequent works. The results that I'll talk about are summarized in this short paper, and we just submitted an article. Or did I? I think I omitted a reference, actually. Anyway, so there's an article up on the archive currently, and then we're about to submit another one on generic lower bounds. Okay, so what is quantum tunneling? So it's a phenomena that goes back to the foundations of quantum physics. So the picture is you have two pockets, two wells, and a quantum particle has equal probability of being located in either of these two identically well-separated, widely separated wells. This is so-called double well potential. And dynamically, the consequences are that if you start with an initial condition which is concentrated in one of the wells, then after some finite time, this initial condition will appear in the other well, in the right well, after some time tau. And this is called a tunneling time, and it's related to a splitting of eigenvalues of the Schrödinger operator, this double well potential. So that's the tunneling time, and if the wells are very, very deep or very, very far apart, then this quantity over here is exponentially small, so the tunneling time is exponentially large. So in this talk, I'm interested in talking about, I'll be discussing lower bounds. First, I'll talk about it in the non-magnetic setting, and then finally in the magnetic setting. Okay. In the non-magnetic setting, there was a very well-developed theory. You could read about it in Landau and Lipschitz, and then the mathematical theory was very well developed by people like Barry Simon and Helper and Sjöstrand in the 1980s. A lot of subsequent work as well. So here, let's get started. So these are the Hamiltonians. These are the main players. Okay, so we have the quantum particle in a single well. So that's Laplace operator plus lambda squared. Lambda is going to be a big number, and V is a potential well. Then there's the double well. So I take this same well and I just translate it along the x1 axis to the left and to the right. And this is my double well potential. Again, lambda is going to be large. And then there's the magnetic variant, where we replace the Laplace operator by the square of the magnetic momentum operator. So minus I grad x minus this over here. This is the magnetic potential for a constant perpendicular magnetic field. This particular gauge is called the symmetric gauge. There's also the Landau gauge, which we'll be working in the symmetric gauge. So the curl of B is the curl of A here is a constant, perpendicular. And this Hamiltonian is referred to as the Landau Hamiltonian. Okay. So it's well known to have flat band spectrum, just discrete eigenvalues of infinite multiplicity. Yeah. Okay, so the overview of the talk is as follows. So this is the energy splitting. I want to get lower bounds for this. And in the regime for the double well potential with very large depth. So first, quantum tunneling always occurs in non-magnetic systems. So this is an exponentially small quantity. And the first result is that it turns out that in magnetic systems, in strongly magnetic systems, you could arrange for configurations, you can arrange for double wells with the property that the tunneling actually vanishes identically. And then the second result is that this is a non-generic situation, that in generic systems, in some sense, if you average over coupling parameters lambda, then there is a lower bound, with epsilon strictly positive. We don't know how to make epsilon go to 0. Yeah. Okay. And then there's some remarks on how one might be able to use this effect to create crystals, macroscopic structures with nearly flat band spectrum, okay, which is a topic of great interest. Okay, and please stop me if there's anything unclear. So let's review tunneling in non-magnetic settings. So we start with the deep single quantum well. We call that lowercase h lambda. The potential V is taken here for convenience to be C infinity. It should have a strictly negative minimum at the origin. And the minimum should be non-degenerate. That means that you'll be able to approximate the potential in the neighborhood of x equal to 0 by something quadratic, so the harmonic oscillator will come in. Okay, so here comes the harmonic oscillator. So let's fix an integer, a positive integer n, and I want to study the first n eigenvalues of this single well Hamiltonian. So the natural thing to do, of course, is to expand about the minimum. So this is an expansion about the minimum. And E lambda is an eigenvalue. And then we could scale. We can scale like this and obtain an operator which asymptotically for lambda large is scale free. This is the quantum harmonic oscillator with this as eigenvalue. So as lambda goes to infinity, you expect the spectrum of this operator to converge to the spectrum of this scale-free operator, which has eigenvalues ej, ho for harmonic oscillators. So these are basically integers, or integers shifted. And then unwinding this, you see that ej is approximately given by this. And the reason why I show this is that in the analysis that we do, it's important that the lowest two eigenvalues of the isolated well be uniformly bounded away from each other in lambda, in the parameter lambda. Okay. So if I look at the lowest two eigenvalues, that would be E1 minus E1 minus, E2 minus E1. That difference is proportional to lambda, and that actually grows with lambda. All I need is for that difference to be of order 1. I need some kind of spectral gap between the lowest two eigenvalues of the atomic well, the single well. Okay. By the way, if we didn't have a quadratic behavior by the minimum, suppose it were flat, like a square well, then the gap distance would be really of order 1. It would not be of order lambda. It would be of order 1. Okay, so now the double well. So these are, remember, a lowercase v of x is compactly supported on a ball of radius a, and so here are two wells, and I take d to be larger than 2a so that they're supported, the supports of these two wells are disjoint. This is a convenience. And I'm interested now in the lowest two eigenvalues, the low-lying or lowest two eigenvalues of this double well Hamiltonian. And this Hamiltonian is symmetric about the line x1 equal to 0. So the low-lying eigenvalues will be symmetric, respectively anti-symmetric about this line. And I introduce this fancy S of lambda as the gap. The ground state is always simple, so this is always a positive number in the non-magnetic case. And we want lower bounds on it. So a theorem is that for the double well, the low energy splitting satisfies such an inequality. E0 lambda is, from the previous slide, it's the ground state eigenvalue. It's the lowest eigenvalue of the atomic Hamiltonian. If the Hamiltonians are infinitely far apart, the eigenvalue would be degenerate, and so you have this degenerate splitting here into the two lowest eigenvalues on either side of the atomic eigenvalue. And then the gap has size which is exponentially small. Okay. It's in the physics literature and was proved in results going back to the 80s. In fact, there's an asymptotic expansion even for the... Okay, so I want to say something about the heuristics of exponential splitting. So first of all, by the variational characterization of eigenvalues of a self-adjoint operator, together with the symmetry of the potential, we have that the eigenstates have these two properties. They're going to be concentrated. I want to minimize this quadratic form, and so the eigenvalues are going to be concentrated, the eigenstates are going to be concentrated near the minimum of the atomic wells. As lambda gets bigger and bigger, they're going to get more and more concentrated. And then the two lowest states are going to be even and odd respectively with respect to x1 equal to 0. And to approximate these states, it's natural to introduce the left and the right, oops, that should be an R there, the left and the right atomic Hamiltonians. So VL is just V of x plus d over 2, and VR, which should be there, is V of x minus d over 2, just the shifted potentials. And then associated with those single well Hamiltonians are going to be shifted ground states. So I take the ground state, I move it over to the left, I move it over to the right well, and I clearly have that relation. And so there's a principle that goes back to the early days of quantum chemistry called the principle of linear combination of atomic orbitals, okay, which says that you can build the low-lying spectrum by taking linear combinations of these atomic states, okay? So this is how it works. I mean, this is the single well, and here is the double well, and right, if I take a symmetric combination, I get something which is a good approximation to the ground state, and if I take an anti-symmetric combination, I get a good approximation to the excited state. All this can be made rigorous. This is the ground state energy of the atomic well, and there's the splitting into the two eigenvalues. And the claim is that this is an exponentially small energy difference. Okay. So the eigenvalue splitting in this analysis is controlled by an emergent quantity. It's called the hopping coefficient. And what is it? What you do is you take the ground state on the left, in the potential on the left, and you look at the overlap integral with the ground state on the right. So this is an exponentially decaying object. This is an exponentially decaying object centered elsewhere, so they'll have exponentially small tails. So it's easy to see an upper bound for this quantity, which is exponentially small. The trick is to get a lower bound for it, and then there's in order to estimate this eigenvalue splitting and therefore the tunneling time, it's good. You want to relate the eigenvalue splitting, that is E2 minus E1, to the hopping coefficient. So one has to get a reduction of this to one quantity to another. And one of the things that one could show is that this ratio approaches 1 as lambda goes to infinity. So to estimate this, to obtain bounds on this, it suffices to get bounds on this, you estimate that this is exponentially small. D is the distance between the two wells, and lambda is the coupling parameter. And that's how it works. Okay. So there are different approaches. Simon used large deviation asymptotics, a probabilistic approach based on the Feynman-Kotz representation, and Helfer-Scherschran used semi-classical analysis. A bit later, in work on graphene-like problems, together with Pfefferman and my former student Lee Thorpe, we produced a pretty elementary argument that didn't make use of the non-degenerate minimum. So we don't get anywhere near the precise asymptotics that are obtained here, but we got something that would work for something that was flat at the minimum. Okay, so now I want to turn to tunneling and eigenvalue splitting in the presence of magnetic fields. And our first question is why? Why am I interested in that? And the motivation is from topological physics that we've heard a bit about, particularly from the lectures of Guillaume and Alexei, and we'll hear about from Alex Watson. So going back to the first observations by von Klitzing of the integer quantum Hall effect and its explanation by Thouless and collaborators, and then subsequent work in topological insulators. So the quantum Hall effect is one where you subject a two-dimensional quantum system, sort of a system with electrons in it constrained to the plane, to a perpendicular magnetic field, and there's an observation of quantized currents. And the explanation of this was given by this group shortly after the experiments of von Klitzing. And their analysis was based on a type binding model for crystals, type binding, a discrete model, a system of difference equations. This is called the Harper model. And the original motivation, begun with a project with Jacob Shapiro, was to understand how do these type binding models, how do these discrete models emerge from continuum models like this, in the limit as lambda goes to infinity, because it's this Harper model which has non-trivial topology that explained the quantized behavior observed in experiments. And with Charlie Pfefferman, we saw that we needed a lower bounds on the magnetic hopping. I'll show you how that comes about. I just want to mention something about the scaling, this particular scaling. You might say, well, okay, why are you taking lambda to infinity over there? So if we take a magnetic field with bounded scaling, then there's a result going back to 1990 by Belisard and Nakamura that says that if you have a magnetic field which is bounded in lambda, then the models that you get in the limit are topologically trivial. Okay, so this scaling has a nice property. It's very natural from a semi-classical analysis point of view, but it also has the feature that you get things like the Harper model coming out. Okay, so how do these type bounding models come about, and how does the hopping coefficient enter? Well, suppose you look at a potential, so this is now the Landau Hamiltonian, and I add a potential which is now not a double well. This is going to be a potential which consists of potential, think of it as compactly supported potential wells that are supported on an infinite discrete set, G. Okay, it doesn't even have to be translation invariant. It could be Z2, it could be the honeycomb lattice, but it could be a disordered discrete set, just as long as the points don't accumulate. Okay, so consider such a potential, and now recall that for the double well problem, the low-lying spectrum was spanned by these two orbitals, and the same trick will be used here. We're going to look at orbitals that are centered at all of the sites of the discrete set G. Okay, but because it's a magnetic Laplacian, we're going to have to use something called magnetic translates that I'll make explicit later on. And this forms a nice approximate basis for the low energy subspace, for the analog of the low-lying spectrum of the 2L model. And when you calculate, so I can introduce the orthogonal projection associated with the span of this, in L2 of R2, and if I look at the projection of the Hamiltonian onto this nearly orthonormal set, then what comes out after some use of yeah, excuse me, using the, yeah, after looking at the various cancellations and overlap integrals, is that you get a single coefficient coming out times a scale-free operator, and this is the magnetic hopping coefficient. Okay, so in order to study the limit of this operator as lambda goes to infinity, if I want to get some limit, I have to divide by rho mag, right? I divide by this coefficient, and then in the limit I get this scale-free object. But I need for this quantity, which in general is complex, it turns out to have a lower bound, right? Otherwise I won't be able to divide and pass to the limit. Okay, so this is how magnetic hopping plays a role in the theory of crystals with topological behavior. Okay, so one could show, right, if there's an appropriate lower bound on the magnetic hopping, then you have a result like this. You divide, you could look at, in the sense of resolve and convergence, you can show that you get convergence to the tight binding. So here Z is anything in the resolvent set of the limiting, the scale-free operator. So for any fixed Z there, you can pass to the limit, like that. Okay. So I have to tell you what the magnetic hopping is. And we'll see that it's an oscillatory integral, a highly oscillatory integral. And the question is, will it have a lower bound? And that's a subtle problem because it turns out to be an oscillatory integral with no critical points in its phase. So if it's an oscillatory integral with critical points, you might be able to do an asymptotic expansion and use stationary phase, but you can't in general here. Okay, so now we go back and start again, but now with the magnetic single well Hamiltonian. So P gets replaced by P minus A, the vector potential, okay? Again, this is a symmetric gauge. The curl of this is a constant, perpendicular. And the magnetic double well is the same thing, just for Laplacian gets replaced by the magnetic Laplacian. And we have this parameter B, which I'll refer to as the magnetic parameter. You can think of it as the ratio of the magnetic effect and the electric potential. Okay. Now, what was the next step? The next step was to take individual isolated wells and to construct orbitals. Okay. So I need orbitals associated with the left and right translates. So this is the left Hamiltonian. This is the right Hamiltonian. And so I want the ground state of the left Hamiltonian. I want to look at that eigenpair and the left of the ground state of the right Hamiltonian and that eigenpair. And so let's write down what phi L and phi R are. And the first thing you want to do is you want phi L to be just a translate, right? Just to translate to the left of the atomic ground state, but it's not. And the reason is that the usual translations don't commute with the magnetic Laplacian. So translations don't commute with this. You need some other kind of operator to translate, and that was observed by Zach in the 1960s, and that's called magnetic translation. So it turns out that this operator over here written in the current context, I call that R hat D, will translate, will commute with the magnetic momentum operator. Okay. So now we know how to construct left and right orbitals. We just apply R minus D over 2 and or R plus D over 2 to the ground state. Okay. And then again, we form orbitals, linear combinations of magnetic orbitals, and those are good approximations of the lowest two energy states of the of the double well. Okay. What about the hopping? Well, this was the formula for the hopping earlier. It's the same formula as before, phi L, VL, R, but now these states are, remember, those are magnetically translated, so they have some kind of complex phase associated with them, and when you work out what that is, they appear in the hopping as this complex exponential, which as lambda goes to infinity, oscillates very, very quickly, and it has no critical points, so no critical points in lambda. So the problem is to bound this from below. Okay. In the non-magnetic setting, B is equal to 0, and one can control this. Okay. So here are the results. Okay. So first questions are first of all, are these two related to each other, as they were in the non-magnetic case, and do they satisfy quantitative lower bounds? So here's a summary of results. So if V is radial, suppose the atomic well is radially symmetric. So I have two circular pockets which are separated. Then there is a bound, a lower bound on the magnetic splitting and on the magnetic hopping, and you have such a relation. But if V is non-radial, if your pockets are, you think of them as being deformed and not being radial, well, it turns out that there are some interference mechanisms through which you can arrange for the magnetic hopping or the magnetic splitting to vanish. Okay, we don't, in the examples that we construct, we don't know if they vanish together, but basically we arrange for this to vanish, and as a consequence, this will vanish possibly for some nearby value of parameters. So these are very engineered, these are systems, these are counterexamples, these are specially engineered systems to take advantage of a kind of cancellation. But it's the sort of thing that in principle you could try to design for. On the other hand, such designs are non-generic. For typical wells, we prove generic lower bounds on these. Okay. Okay. So first the radial case. In a paper with Pfefferman and Shapiro, we showed that if the potential wells are radially symmetric, then we have this relation, as we did for the non-magnetic problem, and a lower bound of this type. The main thing I want to just point out here is that there's a behavior on d squared, not d. In the non-magnetic case, it was lambda d. It's d squared because the Landau Hamiltonian, if you look at the Green's function for it, it involves the harmonic oscillator is clearly lurking here. If I expand the magnetic Laplacian, I'll get a Laplacian minus Laplacian, and there'll be a plus x squared. So there's a harmonic oscillator there, and harmonic oscillator states have Gaussian decay, so hence the d squared. Okay, and then afterwards, using observations that we made, but also using much more, really using precise WKB asymptotics. There were leading order asymptotics were obtained by Helfer and Kachmar and by Leo Morin. Okay. Just a comment on the proof of on the proofs. So here is the magnetic hopping coefficient, and remember V is compactly supported, so V is compactly supported in a ball of radius A about the point minus d over 2, and because of the separation, so the ground state which appears here, the translated ground state which appears here, is being sampled outside the support of this. In other words, excuse me, it satisfies a constant coefficient problem outside, right? Because the potential V is 0 where this is being evaluated. So because of that, we're able to express the ground state outside, in this region in terms of special functions. And then there's a marvelous cancellation that happens. If you make an interchange of order of integration, and then you find that what looked like an oscillatory integral, and maybe you would try to approach by stationary phase or some other oscillatory asymptotics method, it turns out to be the oscillations are gone, and then we're able to apply Laplace asymptotics. Okay, so there's something of a miracle there, and it makes explicit use of the symmetry in order to make this exchange of integration. But in non-radial case, we showed that there's a family of potential wells, and I'll just write it here schematically as, so the potential wells now depend on lambda, right? So things are a little bit, they deform with lambda here. You know, you'd like lambda squared times something independent of lambda, but we take it to be dependent on lambda for now. And there's a parameter y bar, which moves you within the family, and such that if lambda is sufficiently large, you could find values of this parameter y bar in the family such that the magnetic hopping is 0. In other words, tunneling is completely eliminated. So this is something which is impossible in the non-magnetic case. Okay. Furthermore, by varying the parameter y bar, we can actually get the ground state eigenfunction to transition from symmetric to anti-symmetric. Again, something that you don't see in the non-magnetic case. At the degeneracy, what happens is, well, the splitting is 0, and then you have a degenerate eigenspace. The ground state is degenerate in this problem. Okay. So the phenomena appears to be new, and it would be really interesting if one could do experiments of some kind. I want to just give a sketch of what the counterexamples look like. So here, there's a mechanism, and one could draw make lots of examples of this type. But this is a simple example where we have an atomic well. This is the atomic well now. We start with something radially symmetric, and then we decorate it with very, very small potentials. What I'm showing here is the support of the potential. So you have this radially symmetric support on a ball of radius 1, and these little circles here are of size lambda to the -1. And so that we call the big circles, the potential which is supported on the big part, we call that the planet. And these little guys over here are called sophons. And if you've read the three-body problem, then you know that sophons are very, very small objects which wreak havoc. They really have a very big effect, even though they're very small. So that's what, okay. Okay, so, and there are some parameters here. There are the radii of the sophons which vary. There's the distance from the planet to its sophons, and then there's the distance from the centers to the planets. And all of these get tuned in this counterexample because we're trying to do asymptotics. The asymptotics will work like this. We're going to take parameters d1, d2 sufficiently large and fixed, and then we'll take lambda sufficiently larger than a parameter dependent on those chosen d1 and d2. D1 will be like, if this is d, then this is going to be d to the 3/2 or something. Oh, I wrote it over here, yeah. Okay. Okay. So this is so we're talking about potentials like this. Again, if the sophons weren't there, you'd have a lower bound. With these here, this family of potentials is rich enough to force a vanishing of the hopping and of the splitting. Okay, so in a little more detail, so remember the hopping involves the right and the left. The right and the left translates of the individual atomic ground state. So there's some So there's a ground state that's associated with this atomic well, But because we've taken the depth of this well to be very small and the radius to be very, very small, these will be small. When we expand the ground state of this configuration, this will be a perturbative effect. We have to keep track of the errors, of course. So that's what goes on the right and the left side. So let me just remind you of what So you have the left state, and you have the right state, and then you have the magnetic phase. So using the equation for the left state, right? We can rewrite the left state as the Landau resolvent acting on the potential times phi. Just using the equation for the left state. So we're essentially iterating once, so we have this more symmetric form, VR, VL, and then things are wedged in here where K is the Green's function of the Landau Hamiltonian. Okay, so this is the thing that we have to bound below. And so now we look at the potential. The potential has a big part and 4 little parts. And then again, a big part, the right part has a big part and then 4 little parts. So there are 5 parts, and you plug them in. It's a sum of 5 things. And so there are 25 in this particular realization of the counterexample. So you have interaction terms, right? There are terms that come from the planet interacting with the planet. That means that's a term that would have, V of x multiplying V of x centered on the left, V of x centered on the right. But you also have sophons interacting with planets, and left sophons interacting with planets, and right sophons interacting with planets. So you have all these terms, and what we're doing is we're tuning so that the dominant interaction is the sophons of one planet that are nearest to the other planet. So these 2 guys interacting with this planet, and these 2 guys interacting with that planet. Okay, so that's what the tuning of parameters does. And then you have all the errors, and you have to control these. So that one has to work a bit at that. But a key thing to point out is why are these chosen to be very, very small in diameter? Why aren't they just being chosen to be small in depth? We want them small in diameter because of the magnetic. See, we want the effect of the sophons to be large, at least as large as. We want those to be the dominant effect, actually, and we could achieve that by taking these to be very small, because as you see over here on the scale, if x varies over a scale which is smaller than 1 over lambda, this will not be oscillatory, so you won't get a cancellation effect. So that's what motivates these being very, very small in diameter. Okay, so you do the calculation, and then it's the planet, sophon interactions, and you get something like this. Okay. We're able to arrange the calculation so that we get something which is oscillatory plus exponentially small corrections, and the whole thing is exponentially small. But then you see that by varying y bar is this vertical translate, you can force this to move through 0. And that's how the hopping is made to go through 0, and therefore we're also able to make the splitting go through 0 by a kind of reduction process which connects the 2. Okay. So any questions about that? Okay. So there's a bit of fine tuning to be done here. Okay. And as there are other ways to achieve this effect, but this is one of the nice things about this configuration is that one well is just a translate of the other, and there's a certain symmetry to this as well. There's an inversion symmetry which forces the hopping coefficient in this case to be, although it's oscillatory, it's real valued. So we're really, by taking such a configuration, we're working with a real valued function. It's much easier to force a real valued function to be 0 than a complex valued function. We also have examples where you break this symmetry and you could also do the argument, but it requires a winding number argument instead of just a transverse crossing of 0. Okay, and then, but these examples, as I've emphasized, require a lot of tuning, and it turns out that they're non-generic. Okay, so there's the sort of thing, but we think they're interesting because that's really what applied physics is. It's about non-generic situations, not generic potentials. It's making things that have tunable behavior. But generically, we have tunneling lower bounds. So the hypotheses in general are we take V to be C infinity. Maybe the minimum is -1. It's attained at 0 and nowhere else. The Hessian is positive. And this is our double well Hamiltonian. And here is the kind of bounds. There's a discrete set of lambda values such that once you throw them out, you'll get a lower bound if lambda is, lambda has to be sufficiently large. I can't go down to 0. Lambda has to be sufficiently large, and you have this. And so the way we prove this is actually to prove something like this, which is a kind of, if I take this inequality and I take the logarithm of it, and then I multiply by logarithm and then multiply by -1, then you get a logarithmic version of this inequality, which looks like an upper bound now for log of 1 over the quantity of interest. And the claim is that we could prove some averaged statement of this type. And from this, we go to some kind of pointwise behavior outside of a bad set. So just comments on the proof. Let me include the parameter. I didn't say it, but here we're taking the magnetic parameter here is taken to be fixed and sufficiently small. Right? So we fix it sufficiently small, and then we let lambda get big, and lambda is going to be dependent on this. So the key to proving this is to show that the magnetic hopping and the magnetic splitting are analytic functions in a sector, which includes from some point on the real axis out to positive infinity. So there's some complex sector which could get as close to an aperture of size pi, symmetric aperture of size pi, as you like, but we can't go all the way to pi. In order to go if we could go all the way to pi, then we could get the lower bound. We could get epsilon equal to 0. So the analytic properties of this function play a role in getting the right behavior. So, okay. So let me say how. So that's the claim, that it suffices to prove this analyticity. And now, suppose we have that, and we pick a lambda star which is larger than this number. Then remember, from the magnetic lower bounds, from the non-magnetic lower bounds, we have the result. If b is equal to 0, there is a lower bound, and so for that lambda star, it will hold for b sufficiently small by continuity for that particular value of lambda star. So we have a lower bound in the sector for a value of lambda, and we also have upper bounds. Those are much easier to get. Just taking there you get to use just triangle inequality and estimates. So putting that lower bound at a point together with upper bounds everywhere in the sector, one can then use some ideas from complex analysis to show that for B fixed and sufficiently small, you can bound these from below throughout the sector, except on a discrete set. Okay? I could show a lemma at the end, which we use. Okay? So, so it boils down to establishing the analytic continuation of the magnetic hopping and the magnetic splitting, and this relies on the analyticity in an appropriate sector of the ground state itself. Okay, this is for complex lambda. Okay, for that we need to understand the resolvent in the complex plane, where H lambda is the single. We start with the single well Hamiltonian. We have to do the double well also, but this is really the key. But note, this thing does not have an analytic continuation as an operator on L2. The reason for that is that, if you look at X outside of outside the support of the potential, you have the Landau Hamiltonian. And the Landau Hamiltonian is really nasty when complex parameters lambda. In fact, it was shown recently, and I'm sorry, I forget the authors' names. A group showed in the symmetric, in the Landau gauge, in fact, that if you make lambda complex in the Landau Hamiltonian, then the spectrum is the entire complex plane. Okay, so this operator is really problematic for lambda complex. So, I don't know what happened there. Yeah. Anyway, whoops. So what do we do? Let me say. So this operator is the resolvent is not in the complex plane. But what we can do is if you look at the magnetic hopping, let's go back to that. The magnetic hopping is this expression over here, and notice that you don't need the ground state everywhere. You need it really just on a compact set. So it turns out that when you want to construct the resolvent, you have to satisfy a non-homogeneous equation. If the right-hand side of the equation is compactly supported on those functions, it has an analytic continuation. So that's what we have to work on, and that's technical, and we can prove in that way the necessary analyticity of the ground state eigenfunction in lambda in this sector, and the lemma on the complex analysis lemma is that here's my sector. I have an analytic function in the sector. Suppose it's bounded and it has a lower bound at a point in that sector. Then you have such control. Okay, so this is what gets used. Okay, I think, yeah. So I'll wrap it up now and then take questions. So quantum tunneling always occurs in non-magnetic systems, and quantum tunneling can be completely suppressed in engineered magnetic systems, and but generically there is a lower bound. Quantum tunneling does occur, and it appears that the phenomenon is new, and we're talking to physicists. Hopefully, someone could build some version of this. Perhaps not in condensed matter, but maybe in artificially constructed. There are things called metamaterials where people make artificial atoms, and it would be very, very interesting to see this. And it suggests the question suggests that this approach, based on this cancellation effect, it suggests possibly constructing flat or flatter band crystals. Why? Well, if the if you take a double well configuration which has zero hopping, zero tunneling, then if you make a macroscopic crystal, then the eigenvalue will be infinitely degenerate in that case, or approximately so. So you would have a nearly flat band, and so that would be interesting. So, okay, so this all came out, of course, of looking at really the mathematical question of how do you get tight binding models in magnetic systems, and I think it led to some surprises. So it was a kind of an interesting, exciting adventure for us to see out of a sort of a kind of a fundamental math question something with possible practical consequences. Well, that's to be seen. Okay, so thank you.
Okay, thank you for this very nice presentation. We have time for one question or two.
Thanks for a great talk. I have many questions, but let me just stick to one. So, how much flexibility do you have for for where you put these sophons? I mean, somehow you said that you could put them anywhere, but for example, the sophons that are on the far side, are they important at all, or?
Actually, not. So we used this design because we wanted something. We wanted it to be a double well where you take one thing and then you translate it, and you get the same thing over here. Okay, but we could have done this with a more minimal structure. I could have eliminated this, this, and this, and this, this, and this, and all I needed was the inversion symmetry, because that's enough to make the hopping real. And then you could play the same game. But this is a way to achieve a structure which you just simply move over. Like if you had a printer, you would just do like that. So yes, yeah. Okay, yeah. But, yeah, okay, we could talk more.
Any more questions? If not, we thank you again, Michael.
Okay.